Oh, hello, can you explain me what gravity is? It's for a school project. You've come up to the perfect person. My name is Dr. Gravity. Gravity. There was once a very famous scientist called Isaac Newton. He formulated a law called Newton's law of universal gravitation. What? What is this book even of? California road trip? Bah, the book wasn't even very interesting. I'll explain it on the board. Come over here. The theory states that any two bodies attract each other with a force that is directly proportional to the product of their masses, mass 1 times mass 2, and inversely proportional to the square of the distance between them. The constant is called G. Some people even call it Big G. G equals 6.674 times 10 to the power of minus 11. So the equation is like this.
Mass 1 times G times mass 2 divided by the distance squared.
This, in our planet Earth, is equal to 9.8. The units of this are meters divided by seconds squared. Some people come and tell me, I weigh 50 kilos. This is not true. You weigh 50 kilos times 9.8 meters per second squared, which equals 490 newtons. Gravity makes the Earth attract me. I attract the Earth with the same force that gravity attracts me to it, but this force is so insignificant compared to the Earth's mass that it barely moves.
I don't care where you've been. The only thing that matters now is where the night will end. Them bright big lights are shining.
I am super cool. I can move the earth.
You are super egocentric. I can do that too. And if we both do it, the earth will not move.
Dr. Gravity, does mass affect how fast things fall? No, I'm sure.
Them bright big lights are shining on us. That beat is so tight, it makes you wanna get up, get down like there's no tomorrow. Like there's no tomorrow. Like
Dr. Gravity, you were wrong. That is because as object B had more mass, it also had less resistance. As it had less resistance, it went faster. Oh, okay. And what if both objects had very little resistance? Both objects should fall at the same time. Actually, mass affects, but the difference in time is so small we can hardly measure it. In places where there is no air, like a vacuum or the moon, there is no air resistance. This rock and this piece of paper would fall at the same time. I have found a video on YouTube. I'll put it for you. Oh, okay. Thank you. Well, see you later. No, there is more! Oh, okay. What is it? I'll tell you the story. Once upon a time, more than 2 centuries after Newton's time, a new scientist is born, Albert Einstein. He came up with a new perspective on gravity that extended Newton's discoveries. His theory is too complex to explain in this video, so we are only going to see a very basic part of it, the warping of space and time. The white cloth represents the space and time, and the rock in the middle represents a planet that produces a warping with its mass. This warping, or bending down of the space-time, is called gravity. If I let go of the orange ball, which represents a planet, it will start orbiting the bigger one. And why doesn't the Earth just crash into the sun or something? Like the balls in the experiment, they always ended up crashing into each other. To understand that, we need to understand orbits. Imagine this is the Earth, and this is a mountain, and this is me. If I throw a rock from here, it will go like this. If I threw it stronger, it would go like this. And so on. If I throw it strong enough, it would start an orbit and never stop. This can only happen if there is no atmosphere or anything to stop this force. In the moon, we could have a very low orbit. But on the Earth, the orbit would need to be outside the atmosphere. Einstein's theory does not prove wrong Newton's one. It just expands it. Newton's theory is still used nowadays in astronomy, and scientists prefer it because it's much simpler and accurate enough, in most cases. But it does not apply to more complicated concepts like black holes. Scientists are still looking for a theory that can be applied to all scales, from universal to atomic.